Welcome back, everybody, and welcome to Deeper into Maths. This is your mentor, and today we'll be studying an interesting topic of physics, that is nuclear physics. This is an amazing chapter if you see, and if you have an interest in this particular field, then this is a must watch video for you. So, before getting quickly into what nuclear physics is, let us get to know the story of how nuclear physics started. It would not have been possible for nuclear physics to develop so much if there wasn't a World War II. Because during the time of World War II, the American agents and spies got to know that Germany is building an atomic bomb. And at that particular time, Einstein had just migrated to America. So it was like they were in a hurry to build an atomic bomb. And hence, all those things that were being developed, because till the 19th century and the early 20th century, that is the 1900s, the classical mechanics was fully developed. But now the scientists and the physicists were more curious about what the large objects, that is the astronomical objects, that comes under the relativistic physics, that deals with Einstein's equation over there too, with the general theory of relativity. So over there, that development was taking place slowly and gradually, and it still is taking place slowly, even though they seem to think that the pace is very high, but in comparison to the nuclear physics, that pace is very slow, because all those scientists and physicists, they worked relentlessly to make atomic bomb. The governments funded these institutions and research centers to do development and research in this field. And there is this famous Manhattan project that the American government did, that had made the bomb, the fat boy, which was dropped on Hiroshima and Nagasaki, and the small boy, I think so that's the name, but the fat boy is the correct one for the first one. Hiroshima and Nagasaki bombs were developed under the Manhattan Project, and the Manhattan Project included some of the revolutionary scientists that were in America at the time. That included some of the famous names such as Albert Einstein himself. Second comes Oppenheimer, Robert Oppenheimer. He was the commander in chief of the project, and there's a new movie coming out on the physicist himself. So do watch that movie if you wish. And the third person to note is my favorite physicist, that is Richard Feynman. He was also one of the person who was into this, and he just had completed his PhD and was into this. So anyways, that's the story. And now let us also get to know what nuclear physics is. So, yes, I actually started from the bottom below. Anyways, so nuclear physics, as I just discussed, is the study of the small particles. And now the small particles include atoms such as hydrogen, that have only one electron in the outermost shell, like this. There is this one electron, and there is then one proton inside. I'll write it as plus. Or this is the hydrogen atom. Then comes another atom such as helium atom. So there is this helium atom that has 2 plus charges inside, and this is the outer shell that has 2 electrons in it. This is a helium atom. And other radioactive atoms. Yes. So now let us first see the representation of a particular element You might have known this. It is in the form. Oh, sorry. Actually, didn't notice it. Let me just do this straight. This is our helium atom. And now representation of an element that is in the form A X Z, where E stands for the mass number and Z stands for atomic number. Now what is a mass number? Mass number is the is equal to number of protons plus number of neutron, while the atomic number is equal to number of protons, and in stable state number of protons equals to number of electrons. This is something that is important in this chapter. And now let us understand some important things that we would need. Is the mass of a proton is 1.6726 into 10 to the power minus 27 kg. I am writing this just for your information. You can learn the first two digits and that's it. And the mass of a neutron is also somewhat like that, 1.6749 into 10 to the power minus 27 kg. And the mass of an electron is 9.1 into 10 to the power minus 31 kg. So obviously mass of electron is the smallest. Then comes the mass of a proton, and which is then smaller or approximately equal to, I'll write this sign, this is approximately equal to the mass of the neutron. I'll also do this. And this is equal to 1 atomic mass unit. And we'll come to that in a minute again. So now let us first know that the nuclear physics is all about nucleus. And thus we'll be studying more of the nucleus and the decomposition of the nucleus into its other parts, into other elements, just for stabilization and all those things in this chapter. It should be a really fun chapter, and it is very short and quick. Maybe it would be covered in 2 parts or maybe in 1. It all depends. So let us first start with the radius of nucleus. The first thing to know that we do not know how an atom actually looks, and we assume that an atom looks like a sphere. These all are spheres that I have drawn, but we can't see them because we are viewing them from one side. And this line is not a line that we can see. It is an imaginary line. This line, as we can see, is an imaginary line. We have assumed that an electron revolves in a circular path according to Bohr, which we will cover in the atoms. I was to say the atomic physics. So in that video we'll cover about it. So now, first of all, the radius of nucleus. For that we're assuming that our nucleus is a sphere, and this is the sphere. And now that we know that A, that is our E is our mass number. So the mass number is the number of nucleons, we can say. And and so we know that E is the number of nucleons, and that is the atomic mass. So this mass would be proportional to our volume of our nucleus, and we assume that this is a nucleus, and we assume it to be a sphere, and hence we can write that A is directly proportional to 4 by 3 pi r cube, and therefore all these things are constant. So we are putting them into one big constant, therefore A is directly proportional to r cube. Taking cube root on both the sides, e to the power 1 by 3 is directly proportional to r. This is what our scientists got. And now we remove our sign of proportionality, introducing a proportionality constant that we named as r naught e to the power 1 by 3. So instead of highlighting this can be a 1, that is more important, and the value of r naught is 1.4 into 10 to the power minus 15 meter. So this is important, easy till now, and this value is found out just by experimentation. There is no such thing that we can do in finding the constants. Okay, and now let us understand the types of nuclei. There are multiple types of nuclei in order. The first one being isotropic. Isotope, T-O-P-E-S. Isotopes indicate same number of protons. Isobar, two compounds, two elements in their different states having same number of nucleons, that is sum of protons and neutrons is equal. The C1 is isotone, that being C had that the two elements in the different states have same number of neutrons, and then comes isoelectronic, that has same number of electrons, and isomer being same mass number and atomic number. And the example of isomers can be bromine with atomic mass as 80 and atomic number as 35, and this is bromine in their solid form as a metal, and then again bromine as a gas form 8035. Yes, these are isomers. Now let us find out the density of the nucleus. So the density of the nucleus, we know the formula for density is mass per unit volume. We know the mass is A and the volume is 4 by 3 pi r square. And just now we derived that r is equals to r naught power r naught into a power 1 by 3. So now plugging this value into r, we get density is a 4 by 3 pi r naught e power 1 by 3. R naught e power 1 by 3. Oh, sorry. We give here volume is pi r cube. Therefore, it becomes this cube. So I'm writing here a upon 4 by 3 pi r naught cube a. So now cutting this a, we get 3 upon 4 pi r naught cube as the density. And now here we have to notice 3 is a constant, 4 is a constant, pi is a constant, and r naught is a constant, which value I just told you here. So all the things are constant. That means only one thing, that density is constant of the nucleus. So if it is constant, then what is the value of the density? So the value for the density is 1.45 into 10 to the power 17 kg per meter cube. Now see this value for a moment. We are talking about 10 to the power 17. That's a very big number. So that means the nucleons are very closely connected to each other like this. This show indicates us that these are some of the protons and this being some of the neutrons. They are held together so closely. A rough idea of nucleus. Now let's move further. Now the scientists began to wonder that the nucleus of all the elements have the same density. So there is a minimum deflection in the density. So they started experimentation. And now how to judge whether a particular nucleus is stable or not? Because if we were to judge by this density, then density is constant. So we can't judge. So how did the scientists put a criteria to stable and unstable nuclei? They did one best thing, is that they saw the periodic table. So I'll draw a rough sketch of the periodic table to you. So over here, this is the S block. Then somewhere here is the D block. Then over here is the P block. 1, 2. I'm just drawing this as a rough sketch. Oh my god, what is happening? So this is our S block. This is our what? So this is our D block. Then this is our P block. Whatsoever, I'm not drawing it once again. So the thing was that all elements that had Z greater than or equal to 92, and 92 is uranium, so they were all unstable. And that now they started checking the value for N by P. This is the number of neutrons per protons, which can be found out if the nucleus is a stable one, as this is number of neutrons plus protons is Z. Oh sorry, it is A minus Z upon Z, which will give you A by Z minus 1. That is A by Z minus 1. So we can treat it like that. And so after experimentation, I am drawing a rough graph of N by Z that the scientists analyzed and they found out. So here is our N and here is our Z. N by Z ratio, sorry. So N by Z, and if I start plotting, so let this be our line y equal to x. I'll shift it up for mathematical accuracy. And okay, yes, and now I'm plotting the densities. So here is Z equal to 20 and here is Z equal to 81. So if I start plotting, and the values, so the values go somewhere like this, that they are proportional, and then after 20 the graph somewhat goes in this direction and gain a bit here and there, up and down, and then it remains there. So what does this indicate? For Z less than equal to 20, N by P ratio is 1, and for Z greater than, I'll write the range, so it is between 81 Z to 20. Here the N by P ratio is approximately equal to 1.5 or 1.6, and for Z greater than 81, that is from 82 on, all nuclei are radioactive. And we'll end our session for the lecture today, and we'll discuss tomorrow about the types of decays that the radioactive elements do and perform, and how they do that kinds of decay and how all the nucleons are indulged in it. That is very interesting. So please hang on with us. We'll meet you in the next episode. Till then, goodbye and adios.